Welcome back to Introduction to Genetics and Evolution. In the previous videos, we talked about the process of recombination and specifically the sub-process of crossing over. We talked about using the fraction of recombinant offspring to figure out how far apart genes were. In this video, we'll talk about how to leverage that calculation to generate a map using 3 or more genes, and basically to figure out the order genes are along a chromosome without having to get its full DNA sequence. So what if you have 3 genes? Let's say that you have 3 genes A, B, and C. And let's say you know the phase of these genes where all the capitals came from one parent, all the lower cases came from another parent. You have a heterozygote. So there's big A, little a, big B, little b, big C, little c. But in this phase as depicted here, and you're crossing it to the little a, little b, little c, just like what we did in the previous video as a test cross. Okay? Now you know the parental phase is A, B, C, capitals or all lower cases. But what is the linear order? Now what you don't know is this the order? Is B between A and C? Or is it this order where A is between B and C? Or is it this order where C is between A and B? The answer is you don't know. So this is what we're going to try to calculate. So let's look at this. Which of these is parental? Which of the set of possible offspring is parental? Now, these top 2 individuals are definitely parental, right? Because they have the full combination, capital A, capital B, capital C, and lowercase a, lowercase b, lowercase. These other ones all have some sort of recombination event that's happened in there. We don't know the details. Let's put some numbers in there to see what happened. Well, here are some numbers. Maybe you scored either molecular markers or phenotypic markers, and you get these sorts of numbers here. Now, the top 2, the parental types, are always going to be the most abundant. You will nearly always see that. At worst, they'll be equal to the others, but more typically, they will be more abundant if you're looking at genes along the same chromosome. We have a bunch of much rarer types going down. Now, what I'd like to do is I'd like to dissect the problem. Rather than trying to look at A, B, and C simultaneously, let's just ignore C for a minute and just look at A and B. Okay? So just looking at A and B, we can identify the top 2 are parental again. They have big A and big B together, little a and little b together, which matches the phases found in the original parent. The next 2 are recombinant because you have big A with a little b and little a with big B. The next one is actually parental. This is important. This next one is parental-like. It's still big A, big B, and little a, little b, even though we know the C is out of phase with the others with respect to the parents. But again, we're breaking down the problem just to look at A and B. Okay? And the bottom one here is recombinant. Big A, little b, and little a and b are together. So when we add these up, what fraction are recombinant? Well, it's 15 plus 13 plus 1 plus 1. So it adds up to 30. Up to a total of 30. The total here is 1,000, if you add up all those numbers together. So our recombination fraction in this case would be 3%, or 0.03. Okay? So that is the recombination distance between A and B. Okay? So we calculate that. That's between A and B. 3 centimorgans apart, or 0.03 recombination. What about between A and C and between B and C? Well, we can repeat the same process. Let's go ahead and do that. Between A and C, which ones are recombinant? This would be recombinant between A and C. This would be recombinant between A and C. This would be recombinant, and this would be recombinant between A and C. The bottom one would actually be parental for A and C because you see the capital A and capital C are together, or lowercase a and lowercase c are together. So between A and C, we have 18 and 13 is 31, 31 and 15 is 46. 46 over 1,000. Okay? What about between B and C? Which ones are recombinant, which ones are parental? I'll change the color of my diagram here. Between B and C, this would be parental, this would be parental, this would be recombinant, this would be recombinant, because again we have big B, little c, little b, big C. This would be recombinant, this would be recombinant. So in this case, we'd have 20 over 1,000 will be recombinant between B and C. So let's put all these numbers together. There we go. So we have between A and B, we have 3 centimorgans. A and C, we have 4.6 centimorgans. B and C, we have 2 centimorgans. So we can, from this, figure out the linear order of genes, right? What should happen is the distance from one end to the middle plus from the middle to the other end should be about the same as the total distance. Imagine that you're going from, say, New York to Florida. So you have 3 points, New York, Washington, D.C., and Florida. If you add the distance from New York to Washington, D.C., and the distance from Washington, D.C. to Florida, that should be about the same as the distance from New York to Florida. So in this case, we could do that, and we can say, because of this, A and C must be on the outside. So you have to have A at one end, C at the other end, and therefore necessarily B will be in the middle. So this would be the correct order, right? Because here we have distance from A to B is about 3, distance from B to C is about 2. The total of the two is close to 5. It would round up to 5. So now you may be wondering, why don't AB plus BC, why don't those two distances add up exactly, right? Why doesn't it add up exactly to 4.6? Well, the reason is something that you actually noticed when we were calculating these numbers, is that we have two things that we're calling parental, but they're actually recombinant, right? But here at the bottom two, this individual and this individual, we are counting as parental for A and C. But in fact, they're double crossovers. So not only should they be counted, but they should be counted twice. But we didn't do that. So this is why it doesn't quite add up exactly. We'll come back to this in just a second, but first let me emphasize a different point. When you're trying to figure out the linear order of genes, there's a few tricks you can use. First, if all the loci are linked at some level, and I don't mean completely linked, but I mean that they're on, for example, the same chromosome and reasonably close together, the largest two, the combinations which are the most abundant, so it's just what we saw last time with capital A, capital B, capital C, lowercase a, lowercase b, lowercase c, those will always be the original non-recombinant parentals. So that'll help you determine the phase. The smallest two, basically the numbers that are the least frequent, such as what we saw in the previous slide of capital A, little b, capital C, or lowercase a, big B, little c. Those would be the double crossover. Well, why is that? Why is the smallest two the double crossover? Let me go back just to show you that for a second. These down here were the double crossover type. And you see that they were the least abundant among all the offspring. So why is that the case? Well, again, double crossovers, there are basically two things happening together. So in this case, we have the little a, big B, little c as a double crossover gamete. So imagine that you have a 1% chance of recombination between A and B, and a 1% chance of recombination between B and C. Then what would happen is you could actually multiply these two probabilities. So it would be a 0.01% chance of a double crossover. Essentially, you're taking a rare thing and multiplying by the probability of another rare thing to get this double crossover class. They will always be the rarest class from any particular cross. And again, you can identify which marker is in the middle because it will be that rarest class. The alleles at two markers will be parental relative to each other, while the allele at the third will be recombinant. So we could have immediately looked at the previous slide and said, oh, I see that little a, big B, little c is the least frequent category. Therefore, this must be the double recombinant. And if you know it's a double recombinant, you immediately know that this one must be the one that's in it. So we can leverage this. Here's an example. This is not the same as the previous example, although this adds up to 1,000 as well. Look at this quickly. Which one would be parental? Look at this set of numbers. Which two types would be parental? I said the parental group would be the most abundant group. So clearly in this case, most abundant group is capital A, capital B, capital C, and lowercase a, lowercase b, lowercase c. That establishes your phase already. So we know that the person who we're measuring recombination in looks something like this. What is the rarest combination? What are the rarest two combinations? In this case, the rarest two would be these two. So what we said is that this would necessarily be the double recombinant class. Given that, when we look at it, A and B are in the same phase relative to the parents, C is in a different phase. A and B are in the same phase relative to the parent, C is in a different phase. So in this case, we can infer the order is actually A, C, B. And then we can calculate the distance or between these pairs of genes. So why don't you go ahead and give that a shot. See if you can calculate the distance between them, and you can look online to see if you got the right answer. Now let me ask this question. What would it mean if you got map distances like this? Let's say between A and B, you got 11% recombination. Between B and C, you got 49% recombination. Between A and C, you got 50% recombination. What would that mean? Well, there's a couple of possibilities here. Now, it could mean that A and B are reasonably close together, and C is really far away on the same chromosome, right? Just because you have a recombination fraction of 50% doesn't necessarily mean they're on different chromosomes. Could also mean they are on different chromosomes, right? So you could have this, where this is on one chromosome, this is on another chromosome. You could have this, or you could even have this other order. Basically, one point I just want to toss out there for you is that above about 40%, map distances are very inaccurate, and maybe basically 50%. So I wouldn't ever trust, when you're determining an order of genes, any map distance you see that's more than 40%, because at that point you really just have no information. So if you have something like this, where A and B is 11%, B and C is 49, or even 43% or something like that, A and C is 50% or even 45%, basically you don't know how far apart these are. You just know that A and B are linked. So all of the information you have in this case is that A and B are nearby, and you have no idea where C is. C could be really far up this way on the chromosome, it could be really far down that way on the chromosome, or it could be on a different chromosome. I just want to emphasize that because some people use these numbers as though they have this absolute precision to them, but we're actually measuring rare events. So when you get something on the order of 49%, or really anything above about 40%, don't have too much faith in that number. Okay? Well, thank you very much for listening, and I hope you found this enjoyable.